Good afternoon, guys. Welcome to the 32nd lecture of fluid mechanics subject. So, in this class, we have a new topic to discuss, that is turbulent flows in pipes. So, in the last two classes, we have discussed about laminar flows in the pipes and their problems associated with that, right? So, today in this class, we'll see about the turbulent flow derivation and the various problems associated in this turbulent flow. Okay, yes. Yes. So now we'll see what is the introduction of the turbulent flows in the pipes. So we have discussed the definition of what is the meaning of turbulent flow and how the Reynolds number has been experimented based upon this fluid. And also we have seen the characteristics of laminar flows, transition flows, and the turbulent flows. Right? So now we'll see the turbulent flow in the circular pipes, how the reaction takes place, how the velocity distribution changes takes place, and what are the shear forces acting on the turbulent flows whenever the fluid is acting as a turbulent, right? So this is a figure which depicts the various types of flow, whether in the pipes, that is elbows, T's, valves, etc. in the oil refinery plant. Okay, now we see the introduction of turbulent flows in the pipes. So as per the Reynolds number, what is the meaning of turbulent flow? Whenever there is a high discharge of flow in a pipe, whenever the oil medium is dispersed in the water and moving in different directions, we are calling them as a turbulent flow, right? We are calling them as turbulent flow. Now, how the reaction takes place in this turbulent flow, we will see now. Okay, right. So in the turbulent flows, most of the flows in the turbulent, encountered in engineering practice are turbulent forces. So whatever the forces you are occurring practically, whatever the flows you are seeing practically outside, most of them are turbulent flows, right? And thus it is important to understand how the turbulent flows affects the shear stress. So whenever the pipe is experiencing a turbulent flow, along the walls circumference of the pipe, how does the reaction takes place? What are the shear stresses? What are the velocities? What are the forces acting takes place on the circumference of the pipe, right? We'll see these things. Why? Because majority of the engineering applications, majority of the flows outside what you are seeing, the water from the tap, the water from a pipe, right? The water flow in open canals. So these are majorly experiencing the turbulent flows, Now, the turbulent flow is a complex mechanism. The turbulent flow is a complex mechanism dominated by fluctuations, and it is still not fully understood. So it depends upon the criteria, depends upon the application, depends upon the channel flow. It is a circular flow or rectangular flow or an open flow or a closed flow. So that fluctuations is not fully understood in the turbulent flow, right? In the turbulent flow, it is a complex mechanism where the fluctuations we are getting in the turbulent flow, it is not completely understood. Why? Because in the turbulent flows, the velocities, the shears, the velocity, and the force are totally independent with respect to the applications what you are using. Now, we must rely on the experiment, some sort of experiment should be done, and the empirical corrections developed for various situations. For example, so if you see this experiment, the intense mixing of the turbulent flow brings fluid particles at different momentums into the close contact and thus enhances the momentum transfer, right? So if you take an experiment of the closed contact, if you see the balls, the liquid particles are balls colors before turbulence, how the formation of balls is there, and after turbulence, how the balls are shuffled. So see here, you are having a brown color balls at the top surface. At the second surface, you are having orange balls. On the third surface, you are having a blue colored balls. On the fourth layer, you are having a red color balls. So whenever there is no discharge, whenever there is no force, whenever there is no velocity of the balls are remaining as it is, right? So whenever you are getting an impact or a high discharge of flow or a high discharge of impact through air or a gas or a fluid, so the balls are taking in different directions. Here the balls are shuffling in different directions. Thereby see how the top surface layer, the middle layer, the third layer and the fourth layer are totally disturbed, and the balls are randomly arranged in this phenomena. So this is happening in case of fluids also, right? Yes. Turbulent flows is characterized by the disorderly and rapid fluctuations of swirling regions of the fluid called eddies throughout the flow. For example, if you see in a canal, for example, if you see in a Guntur and Canali, Repal or these areas, we can see all channels. So, Pilla Kalola antam. So, in this rainy season, you can see all the canals are filled with water. So, if you see some canals flowing with very constant velocity without any disturbances. But if you see some sort of canals where you are having ups and downs in the canal area, you can see turbulence flows, you can see some sort of eddies. Eddies means simply in this term we are calling the swirling action of the fluid. Swirling region. For example, మీరు కాలువలు చూసినప్పుడైతే ఎక్కడన్నా బయట కాలువలు చూసినప్పుడు water is flowing in a normal phenomenon. Water is flowing with a normal phenomenon. At some sections, the water అనేది అక్కడక్కడే తిరుగుతూ ఉంటుంది. అక్కడక్కడే తిరుగుతూ అక్కడక్కడే you can get some disturbances in the water areas, water bodies. Depends upon the where application you are seeing. It may be the wall surfaces of the canal or the center of the places or somewhere of the places. Then what we can say here you can see some sort of eddies are generated in the flow, right? These fluctuations provide an additional mechanism for momentum and energy transfer. Already the water is flowing in a turbulent flow, right? Turbulent phenomena. In that only we can see some sort of rough structure where the swirling regions of the fluid occurs. This is called as eddies, right? These fluctuations, additionally we are getting some mechanism of momentum and energy transfer. Thereby what happens, we cannot say exactly what's happening in the turbulent flow, right? Next, in the turbulent flow, the swirling eddies transport, what will transport the mass, the momentum and the energy to other regions of flow much more rapidly than molecular diffusion, greatly enhancing the mass, momentum and heat transfer. So this will give the changes in the mass, momentum and heat transfer. As a result, the turbulent flow is associated with much higher values of friction, heat transfer, mass transfer coefficient. Thereby what happens? Normally whatever the water is going with a normal velocity in a turbulent flow, whenever the additional swirling regions happens in the water body, automatically the friction develops with high values and also heat transfer takes place, mass transfer also takes place, right? Next. So if you see the experiments here, the water exciting, how the water is reacting whenever it is flowing in a pipe. So see here, with an experiment, you have a wooden stick, you have a hinge, you have a screws placed, and you have a transparent pipe placed at some point at the edge of some medium. Now, if you see the figure A, what happens to the figure A? The laminar flow at low rate. So you can see a constant flow of water is flowing, simply the constant velocity, constant flow, which is nothing, experiencing a laminar flow. It is a laminar flow or viscous flow. So we can call laminar or viscous flow, right? Laminar flow or viscous flow. Next, see the figure B. What's happening here? If you see the figure B is a turbulent flow at high flow rate. So here the discharge is very high. Thereby, whenever the discharge is very high, the water, see the velocity, how it is flowing, making an arrow. Here, see how it is not going in this direction. It is moving at a high velocity, experiencing a turbulent flow rate. Now, if you see the diagram C, so see the design of water here and see the design of a water at this point, right? So the section C, the same turbulent flow, but with short shutter exposure to capture the individual eddies. So దీన్నే మనము, so if you are exaggerating and seeing with some sort of camera trick, how the water is making some sort of disturbances in the layer. See the layers, see how the layers are forming, making the short disturbances. Akkadakkade it is making some short disturbances, thereby you can see some small areas where the region is forming. So this is simply nothing but the forming of eddies, right? So this is the small experiment can be done about the turbulent flow, right? Next. Now you are doing an experiment by taking the time t with respect to the length, right? Now if you see the figure, like you see the pipe flow, cross section pipe flow, how the water is flowing in the pipe, how the reaction is taking place, right? So if you take a graph between the velocity and the time t, so the velocity u bar is making fluctuations, depends upon the regions of area in the water. Thereby these eddies are forming here, right? Next, the laminar component accounts for the friction between the layers in the flow direction. How it is experiencing the friction? It is experiencing the friction layers between the flow direction. When coming to the turbulent component, accounts for the friction between the fluctuating fluid particles and the fluid body. So it accounts the friction between what? The fluctuating fluid particles and the fluid body related to the fluctuations components of velocity. So it is experiencing the friction between the fluctuating fluid. So if manaki fluid emoutundi, here the fluid is fluctuating, so it's the boundary anukunte. So here the water is fluctuating when compared to the laminar flow, right? So it is experiencing the fluctuating fluid and the fluid body, right? So that's why the fluctuations, if you see the graph with the velocity and the time t, you can see u is equals to u bar plus u dash, right? And u dash is the distance of the change, okay? Fluctuations of the velocity component u with the time at the specified location in the turbulent flow it is showing. Then the velocity profile and the variation of shear stress with radial distance of the turbulent flow in a pipe is given in this direction, is given like this. So if it's a 0, the tau laminar flow is flowing in this way, whereas the turbulent flow is moving at this direction. Therefore, what is the total tau? Total tau is simply tau total is equals to laminar plus turbulent flows. Tau total is laminar plus turbulent flows, right? So we can call this as the shear stress. So the shear stress of the total shear stress tau total is equals to shear stress of laminar plus shear stress of turbulence. Therefore, shear stress tau is equals to laminar flow plus turbulent flow. Keep this in mind. Next, so if you see the u, if you see only one person, okay. So if you see the u velocity u bar plus u dash, whereas average value is u bar. Fluctuating component, so there is a fluctuating component, u dash is a fluctuating component. Therefore, the velocity v is equals to v bar plus v dash. Therefore, the pressure p is equals to p bar plus p dash. Therefore, the total turbulent t is equals to t bar plus t dash, right? Next. So if you see the shear stresses in the turbulent flow, right? The shear stresses in the turbulent flow. So the shear stress in the viscous flow is given by the Newton's law. Tau is equals to mu of du by dy. Whereas in the turbulent flow, how it is given? In the turbulent viscous flow, turbulent shear stress minus rho into u bar into v dash bar. That is the turbulent shear stress. So the terms, whatever you are using, minus mu or minus mu dash square is called Reynolds number. So if you make a graph between u and y making a small component of a liquid, taking a small component of liquid in u direction u dash and rho v velocity direction, you can see the turbulent shear turbulence is equals to minus mu dash v dash bar, that is equals to u of dou u by dou y. So this is a turbulent shear stress. So the turbulent shear stress is equals to mu into dou u by dou y, where this one is a shear stress due to viscosity. The shear stress due to turbulence is equals to mu of dou u by dou y. Therefore, what is mu t here? The mu t is eddy viscosity or turbulent viscosity. So eddy viscosity or turbulent viscosity accounts for momentum transport by turbulent eddies. Okay, na? Right. Therefore, the total shear stress is equal to tau is equals to mu plus mu t of dou u by dou y. So mu t. So what is mu t here? Mu plus mu t. So that implies rho of v plus vt dou u by dou y, that is total shear stress. So this is the turbulent shear stress, this is the total shear stress. Okay, initial to final. Therefore, vt is equals to mu by p. Therefore, kinetic eddy viscosity or kinematic turbulent viscosity, also called as eddy diffusivity of momentum, right? So taking this one, tau turbulence is equals to mu t dou u by dou y, that is equals to rho of L square into dou u by dou y square. Now what is L here? The length, the mixing length, that is Lm, related to the average size of the eddies that are primarily responsible for mixing, right? So if you see the graph here, the laminar flow graph, the velocity gradients at the wall of the pipe, and thus the wall shear stress are much larger for turbulent flow than laminar flow, even though the turbulent boundary layer is thicker than the laminar one of the same value for stream flow velocity. So if you see the graph on the turbulent flow with respect to u to v, so the turbulent flow is making a angle in this direction, right? That is dou u by dou y is equals to v is equals to 0, y is equals to 0. Whereas if you see the turbulent flow, it is making a constant line at some point, and it is making a curve, and it is making a larger distance to the y-axis. Therefore, the molecular diffusibility momentum V is a fluid property, and the value is listed in the fluid handles. So eddy diffusivity Vt, however, is not fluid property. The value depends upon the condition, right? So in this way, if you make a graph for dou u by dou y, the laminar flow is looking in this direction, the turbulent flow is looking in this direction with respect to the mixing length. So very few came to the class. I don't know why. How the maximum ఎలా చెప్తుందో మీకు అర్థం కావట్లేదు. How many students are coming for max class, CVSM and my class? Okay, no issues. Syllabus should be completed. Now, if you see the turbulent velocity profile. So you can choose a turbulent flow, how it is making a graph. Here also you can see, then exaggerate just there, the graph will be looking like this, right? Now, in the laminar flow, how the velocity profile is moving. So laminar flow which one derivation just we have seen the R radius average velocity. It is making a action at the center point of the center line of the pipe, and it is disclosing in this way. The velocity profile in a fully developed pipe flow is parabolic in laminar flow. So laminar flow, what type of arc we are getting? We are getting a parabolic. So keep in mind, for a laminar flow, The profile is parabolic, but much fuller in turbulent flow. Note that QR in turbulent case is time average velocity component in axial direction. The overbar on mu has been dropped for simplicity. See here in the turbulent flow, it is making a direction as compared to the laminar flow. Here, the turbulent layer is forming at this point, to the center action. That is a turbulent layer. At this point is overlapping. This one is a buffer layer. This one is a viscosity layer. How the profile is changing step by step. So the layer, how it is showing, see here, viscous layer, buffer layer, overlapping layer, and finally turbulent layer. Here also the same thing goes in reverse direction, right? Turbulent flow, overlapping flow, buffer flow, and viscous flow. Like this, we can see the turbulent flow profile. So if you get a question, describe the turbulent velocity profile. So you have to draw this figure simply by showing the layers. We are having 4 layers in the changing from laminar to turbulent. That is viscous layer, buffer layer. Buffer layer means viscous layer nunchi turbulent overlapping viscous layer nunchi turbulent flow ki convert avutunnappudu we require some extra layer, that is a buffer layer. Thereby this buffer layer is converting into overlapping. Finally we are getting the turbulent layer. Got it? Next, the very thin layer next to the wall, very thin layer next to the wall of the pipe where viscous effects are dominant. Viscous effects manaki ekkuvaga unnappudu, that is nothing but viscous fluid or laminar or linear or wall sublayer. Wall ante enti? That is nothing but pipe inner surface. So circular pipe or square pipe, whatever the pipe, wall యొక్క ఇన్నర్ సర్ఫేస్ కి వాటర్ రెండు కాంటాక్ట్ అవుతున్నాయి కాబట్టి at that point you can see some sort of friction, momentum, energy, right? So the very thin layer next to the wall of the pipe where the viscous effects are dominant, ఎక్కువ ఉంటే, that types of things you are calling them as viscous fluid. So here you can see the first one is a viscous fluid. So ఈ layer, ఇక్కడ నుంచి ఈ layer, so this layer is the gap is nothing but a viscous layer. Next one, the velocity profile in this layer is very nearly linear and the flow is streamlined. Next to the viscous layer, the buffer layer in which the turbulent effects are becoming significant but the flow is still dominating the viscous effects. So ikkada em cheptunnaru, in this buffer layer, small buffer layer, it is converting from viscous layer to the more discharge layer, that is a turbulent layer, but still acting in the form of viscous layer only, right? The buffer layer where the turbulence effects are becoming significant. So turbulence layers అనేవి ఇక్కడ చేంజ్ అవడానికి ఎక్కువగా అవకాశాలు ఉన్నాయి కాబట్టి it is becoming as a turbulent buffer layer but still dominating the viscous effects, right? Next, third one, above the buffer layer we have the overlap or transition flow అంటున్నాం. It is called as inertial sublayer. సో మనకి లామినర్ ఫ్లోకి టర్బులెంట్ ఫ్లోకి మధ్యలో ఇంకొక లేయర్ ఉంది, దట్ ఈస్ నథింగ్ బట్ ట్రాన్సిషన్ లేయర్. ఎక్కడైతే మనకి ట్రాన్సిషన్ పాయింట్ జరుగుతుందో, ఎక్కడైతే ట్రాన్స్ఫర్మేషన్ ఫ్రమ్ లామినర్ టర్బులెంట్ ఫ్లో ఈస్ టేకింగ్, ఈస్ నథింగ్ బట్ ఓవర్లాపింగ్ లేయర్. అంటే ఓవర్లాపింగ్ అంటే ద లామినర్ ఫ్లో ఎక్కడైతే టర్బులెంట్ ఫ్లో ఫామ్ అవుతుందో, ట్రాన్సిషన్ ఫ్లో ఎండ్ ఏమవుతుంది, స్టార్టింగ్ ఆఫ్ టర్బులెంట్ ఫ్లో, రైట్? సో ఈ రెండు ఎక్కడైతే మీకు ఓవర్లాప్ అవుతున్నాయో, దట్ టైప్ ఆఫ్ లేయర్ we are calling them as overlapping layer or inertial sublayer, in which the turbulence effects are much more significant but still dominant. Okay, next, so that is this one, overlap layer, e point, right? Next, above that is a outer layer, that is turbulent layer, where the remaining part of the flow in which the turbulence effects dominate over the molecular diffusion, that is the viscous effects. ఎక్కడైతే మనకి viscous effects dominate చేస్తూ turbulent flow particles మనకి ఎక్కడైతే కనిపిస్తున్నాయో, that layer we are calling them as a outer or turbulent layer. Got it? So these are the 4 layers. So if you got any theory part in the question, you can draw the graph, you can draw the figure like this profile, and you can explain those 4 layers. Okay, next. Now, the stress at the wall is equals to mu of u by y. That is equals to mu is equals to rho into v u by y, or stress at wall divided by P is equals to Vu by Y. Therefore, mu U star is equals to root of wall shear by rho, that is friction velocity. Therefore, viscous sublayer is equals to U by U star is equals to Y of U star by B. That is law of the wall. Then the thickness of viscous sublayer Y is equals to 5 VU, that is 25 VU sigma. The thickness of the viscous sublayer is proportional to the kinetic viscosity and inversely proportional to the average flow velocity. Therefore, V by mu, velocity by mu, is U star is equals to viscous length, is used to non-dimensionalize the distance y from the surface. Therefore, non-dimensionalized variables y plus is equals to y u star by v and u plus is equals to u by u star. So, but example will not get this type of things. So we'll ignore this one. Then the logarithmic law u by u star is equals to 1 by k integral v u star by v plus t. So for the overlapping layer, this is the thing. U plus is equals to 2.5 in y plus plus 5.0, whereas the outer turbulent layer is equals to 2.5 in r by r minus r, which is a velocity defect law. Right? The deviation of velocity from the center line value u max minus u is called velocity defect. Therefore, the power law velocity profile u by u max is equals to y by r 1 by l. Hope you are understanding. So majorly in the turbulent flow, you can see how the velocity profile action takes place and what are the formulas associated with the turbulent flow with respect to the mass energy moment. Right? Next, the types of fluid flow problems. How the fluid flow problems are arised based upon the types. Determining the pressure drop or the head loss. So head loss and pressure drop anna okate. So first determining the head loss, where the pipe length and the diameter are given for a specified flow rate. Okay, na? So there you should be specified the pipe length and the diameter given for the specified flow rate. Right? That is problem type. First one on the pressure drop flow. Given what is given, the length of the pipe, the diameter of the pipe, and the velocity of the pipe. Then what is it? What is the thing you have to find? Delta P or HL. So this box meer gurtu pettukondi. What are the types of fluid flow problems you will encounter? Means the first case, whenever you have to find the pressure drop or a head loss under delta P or head HL. If you want to find, so what is the given data? The length of the pipe, the diameter of the pipe, and the velocity of the pipe or flow rate. Next, second one. Determining the flow rate when the pipe length, diameter are given for the specified pressure drop. Second case law. So given data length undali, diameter undali, delta P unde, you have to find the flow rate, right? Next, third one. Determining the pipe diameter D and the pipe length and the flow rate are given for the specified pressure drop. So in the third case flow, when the length is given, delta P is given, velocity is given, we have to find the pipe diameter. So these are the three types of problems encountered in the pipe flow. So a pipe flow aina sare, it may be the laminar or turbulent. These are the three cases you have to, right? So to see declarations of head loss, flow rate, and diameter calculations, right? So according to the Moody chart, so Moody is one of the scientists based where he has given the various types of velocity flows, the stream flows, and based upon the scientists, he has given some chart. So based upon the chart, the head loss formula and the flow rate formula and the diameter formula are given in this way. Then what is the head loss? HL or delta P. HL or delta P. So if you see the HL, head loss, 1.07 V square into L divided by G into d to the power of 5. Integral of this one is E by 3.7 D plus 4.62 into VD by velocity into 0.9 power floor brackets minus 2, where 10 to the power of 6 is less than E by D less than 10 to the power of minus 2. That is Reynolds number 3000 is less than Reynolds number less than 3 into 10 to the power of 8 for the head loss. Then if you are seeing the velocity or a flow rate, capital V is equals to minus 0.965 root of G into D to the power of 5 HL by L into 0.5 integral E by 3.7 D plus into 3.17 into V square by L divided by G T cube HL to the power of 0.5, where this value is RE greater than 2000, right? Next, third case, diameter D is equals to 0.66 into e to the power of 1.25 into L into V square divided by G into HL to the power of 4.75 plus V into velocity 9.4 into L by GHL to the power of 5.2 into 0.04, right? So these are the three values whenever you are finding some sort of problems, right? So you are having few more problems so that we can complete within a given time, right? Now see the problems based upon the formulae. So see here, determining the head loss in the water pipe. So head loss HL panukundam ee question lo. So what is it given here? The water at 60 Fahrenheit delta, the value is 62.36, mu is equals to 7.536, is flowing steadily in a 2-inch diameter horizontal pipe made up of stainless steel. So the material is given as stainless steel and the diameter is 2-inch diameter at the flow or rate of 0.2 feet cube per second. Determine the pressure drop, head loss, and the required pumping water out input for the flow over 200 square long section of the pipe. Okay. Now, so if you see the given figure, the pipe, horizontal pipe, the pipe diameter is 2 inches, and the velocity, the flow rate is V is equals to 0.2 feet cube per second. So the medium is water and the length is 200 feet long. Then what are the properties? The density of dynamic viscosity of water rho is equals to 62.36. ఇక్కడ ఎంత ఇచ్చాడు? Density of water 60 degrees Fahrenheit లో 62.36 ఇచ్చాడు. Mu is equals to 7.5 ఇచ్చాడు. Now what is the thing you have to find? We have to find the problem, the flow rate, the pipe length and the pipe diameter have to be known. So flow rate should be known, pipe length should be known, and the pipe diameter also. First we do the average velocity. First we do the average velocity and the Reynolds number to determine the flow. Then according to the given data, V is equals to flow rate by area. So flow rate divided by what is the area? Pi d square, means pi into d square by 4. So what is the flow rate? 0.2 divided by pi into What is the D? 2 inches అన్నాడు. 2 inches అంటే ఫీట్ లో కన్వర్ట్ చేసుకుంటే 2 by 12 feet అంతే కదా, కన్వర్టింగ్ ఇంటూ ఫీట్. సో 2 by 12 feet whole square divided by 4. So that is equals to value 9.17 foot per second. Now what is the thing? RE you have to find, Reynolds number. So the Reynolds number is equals to rho into VD by mu. And what is the rho according to the given data? 62.36. V is equals to 9.17. D is equals to 2 by 12 divided by mu is equals to which one you have to write. So the mu value is whatever the given question value, that is 7.536 into 10 to the power of 4. Right? So what is the value you are getting? The value is 1,26,400 is a Reynolds number. So which is obviously a turbulent flow. Then RE is greater than 4,000. RE is greater than 4,000. The flow is turbulent. So automatically the flow is turbulent. The relative roughness of the pipe is estimated according to the table. According to the table, P by D is equals to 0.442. Right. Now the friction factor according to the Moody's chart, 1 by root F according to the Moody's Clockering equation. So 1 by root F is equals to minus 2 log E by D by 3 by 7 plus 2.51 Reynolds number into root F. Therefore 1 by F is equals to minus 2 log value, substituting values. So directly we are getting the formula. Delta P is equals to delta PL, that is equals to L D L by D rho into V square by 2. So applying F is equals to 0.0174. Under this equation, the friction factor is determined to be. So ivarni manaki data books lo ivarni they will provide, or it will be assumed in the question only. Therefore F into then what is L? 200 feet divided by 2 by 12 into rho is equals to given question V is equals already we have derived by 2. Then the delta P is equals to 1700 lb feet per feet square, that is equals to 11.8 pounds per inch, pound second per inch. Then what is the head loss HL? HL is equals to delta PL by rho G, that is equals to delta PL is equals to F into L by T V square by 2G. Right? That is equals to 0.0174 into substituting the values, L value, substituting the 2 8G value, substituting the 2 into G value, we are getting 27.3 feet. The head loss is 27.3. Right? Next. Therefore, the weight of the pump is V into delta P. So V is known, that is 0.2, and delta P is 1700. Delta P is 1700. We are getting 461 watts. Therefore, the power input for the amount of 461 watts is needed to overcome the friction losses in the pipe. Got it? Next. So in the next case, we'll find the diameter of the air duct. Diameter of the air duct. Okay. So if you see, the heated air at 1 atmosphere and 35 degrees is to be transported in 150 meters long pipe duct at a rate of 0.35 meter cube per second. Okay. If the head loss in the pipe is not exceed 20 meters, determine the minimum diameter of the duct. So here what you have to find? You have to find the diameter D. So mundi case lo manamu head loss konukunnam, ikkada manamu diameter of the air duct we have to find. So here already the data is given as an input, and so what are the properties to be given? The density is given, the dynamic viscosity is given, the kinematic viscosity of air is also given. Then the density is 35 point C, that is the density of air at 35.C, the density, the dynamic viscosity and the kinematic viscosity of air at 35 degrees are, so manaki ichchadu the question lo, rho is equals to 1.145, mu is equals to 1.895 and v is equals to 1.655 into 10 to the power of minus 5, right? Next, then, so what is the thing you have to find? So v is equals to b by ac, area, v by a into pi into d square by 4. Substituting this one, we are getting the value. Therefore, Re is equals to Vd by V, that is Vd by the V value, this one. Now, 1 by root f is equals to minus 2 log. So, this is a formula for that. Okay, so up to here. So, substituting this one, we are getting, is also a formula for head loss. Therefore, f 20 meters is equals to f of this one. So, finally, the d value is 0.267 meter. F is equals to given, V is equals to given, Re is equals to, we have to find. Therefore, the d value is equals to 0.66 into applying this formula here. So, substituting all the values, E 0, L into V 1.65 plus this value's length is equals to 150 divided by 9.81 into 20 meters, the power of 5.2 into 0.04. We are getting the value 0.0271. Got it? So this is the diameter of the pipe with the length of 150 meters. Then determine the flow rate, that is a V. So the same question, now the duct length is doubled. So the duct length 150 unadi, length is doubled while the diameter is maintained constant, same the constant. Now if the total head loss is not remain constant, determine the drop of the flow rate. Now same formula, V is equals to V by A area of the circular pipe, V by pi d square by 4, that is equals to V is equals to V divided by diameter of AC. Find V. Therefore, Re is equals to Vd into V. Therefore, Re is equals to V this one into d diameter divided by small v, what is given in the question. Therefore, applying the same formula, so we are getting this one. Therefore, the head loss is equals to F into L by D V square by 2G. Therefore, F is equals to V naught 20 meters. Here F is to F A into L is equals to doubled kabatti 300 divided by 0.267 into V square by same thing. So V velocity is equals to flow rate is equals to 0.24. F is equals to this one. V is equals to this one. R is equals to this one according to the table given. Therefore, V drop. Therefore, the velocity drop is equals to world velocity minus new flow rate. That is 0.35 minus this new one. That is 0.11 meter cube per second. Got it? So like this, you have to find the velocity drop for the circular pipe for the same values. So with this, we'll stop the class. I think the time is up. So we'll continue the class to the next session.
Yeah.
Check. Hello. Yes, we'll continue the class in the next session. So I have the class at 3:10 for your seniors. Once the video is uploaded in the class, and yeah, in the YouTube, I will upload this link in your group. Just open. Those majority of people are not present in this class, but open the link and just view it. What happened in this class? Okay. Thanks for listening to the video. Thank you.